recording. Excellent. So this morning, I got a chance to process homework 1. You should be able to see your scores if you submitted it. Not everyone has finished, as expected. I think it's only happened once or twice in my life that everyone turned it in on time, but that's okay. If you didn't turn it in yet, that's fine. It's 2 points off between now and the end of the semester. At some point, please turn it in and you can get your credit. If you're looking at your scores and you're wondering why you missed what you missed, I'd be happy to go over that or answer individual questions or small groups amongst people who've already completed it. Otherwise, I unleashed homework 2 to the TAs this morning. So I expect you have not finished it yet, Vladimir, even for you. He's like, I had another class. Yes, he did. So I will let you know when that is going to be available to you, as well as when the due date's going to be. I'm waiting to see how far we get today and what I can patch through by recording separate videos versus what I can't. My general philosophy is to have at least a week after we finish a topic before you're responsible for the homework on it. But what you can be doing next week, so I have office hours on Monday as usual, not on Wednesday, and then no class Tuesday or Thursday. Vladimir, are you planning on having office hours next week as usual?
Of course. Yeah.
Of course, he says. Okay. I have not confirmed that with 10, who is not having office hours today, by the way, as announced in email, but I will let you know once I know all of those things. What you can be working on for sure is formative assessment number 3, which is a different animal. So this is a Word document that I want you to download. It looks like this. So this is another vocabulary exercise, notation in particular. So I want you to complete each of these blank boxes. So for instance, model parameters, fixed effects, I would want you to list as many synonyms as you can think of in this box that go with that idea. And then within each of these models, pick out which terms are the fixed effects and what they mean. So for instance, in a general linear model, I only have a fixed intercept. If I have no predictors, then the fixed intercept is just the mean of y. So I would write down beta 0, mean of y is what these are. The second row is terms that will have level 2 variances in their interpretations. So all the things that you know of that go with level 2 can go into this box here as synonyms. And then within these equations, which of these terms is going to have a level 2 variance associated with it? So you'll pick those out and define them. And then which terms have level 1 variances and what do they mean in each of these cases? So this one, I would like you to submit it under assignments in ICON as just this document, and I will look through them and make sure that they're okay. Let's see. I will post an answer key for this one. So we will go over it, and if you didn't get everything completed exactly right, no worries. I will release the answer key once we're all done. 2 points for giving it your best try. Okay? Okay.
Yeah. So I'm curious, in your kind of experience with publishing and stuff, are the equations what a lot of journals want, like as you're describing what you did, or is it okay to just, we did this thing, especially if it's maybe not like a quant-focused journal, where this may not necessarily mean anything to people?
Yes, great question.
Not that I'm saying it doesn't mean anything.
May not, yes. I appreciate the conditional. So the question was, when you write papers, would you put this kind of equation stuff in, or would you summarize it verbally? And I think the answer depends very much on what kind of journal it is and who you're writing for. So if you're trying to publish a psych methods paper, for instance, which is one of the top quantitative psychology journals, and you're writing about, multi-level models and you don't have an equation in there, they'll be like, where's the equation, pal? Like, this is psych methods, you better bring your A game. You better have words that go with it, though, because psych methods is read by a lot of people who want to become better at methodology. If you were to put this in Psychometrica, they don't care about words. You can just put the equations in. It's like QED, good luck. For a more applied journal, I usually would not put an equation into the manuscript, but I would often do a supplement that has more details about the analyses, as well as potential, like, here's the equation for this result, for this result, for this result, so that there's more transparency. But yeah, I have put them in papers before and had the editors say, no, take that out. No one knows what that means. So it depends is the answer, I think.
All right.
But to someone who's reviewing your paper, I think the equation makes it clearer what the model says, so long as it's correct. Words sometimes can lead to ambiguities.
Yeah. Okay.
Also, what I put in supplements is code, because that can help get your paper cited if you can provide templates for how you did things that other people who may not know how can follow. So, all right, other questions on this or other stuff? All right, so this is the Monday, what's the date? The 14th. So a ways from now. So you can pretend this doesn't exist, or you can get it done ahead of time and then pretend I don't exist. Take your pick. I will let you know what once I have a more concrete plan for videos to watch, have them recorded and posted and all of that stuff. In the meantime, we started talking about random slopes and stuff like that, right? Okay, basic vocabulary drill. What's fixed mean in this context? The constant part. Yeah.
Level 1.
Level, not necessarily levels. So fixed effects can be at level 2 or level 1, but the term fixed itself means that part's a constant.
I got you.
Yeah, it doesn't have an I subscript. That's the part that everyone shares in generating some kind of prediction. So fixed means it's a constant that everybody gets. What does random mean?
Everybody gets their own.
Everybody gets their own. So that would be the U's in the equation that do have I subscripts, because UI is for one particular individual. What we keep track of, though, is the variance across people in level 2. So level 2, let's do it again. Inter-individual, between person. Random effects, variances and covariances, live in the G matrix. Macro. What else am I forgetting? I think that's all of them. Am I forgetting any on the list? If I go with random intercepts, I'd say that's also cross-sectional, because that's like a mean difference that would have been there if you had one occasion. That means level 1 then, to complete it, is residual variances and covariances of the E's around the lines for each people. Their variances and covariances live in the R matrix. Intra-individual, micro, time-varying, longitudinal. All those words go together. So there's your synonym boxes. You can transcribe. So yes, the idea here is that beyond just having a fixed and random intercept, we can have fixed and random slopes related to change over time. In this example, we're just starting with straight linear because that's the easiest case, and it works well for studies that only have, say, 2 or 3 occasions. In the next unit, we'll explore kinds of nonlinear and discontinuous change, and that will take quite a bit to get through. Unit 6 is a long time. Notation, do we want to go back over that a bit? Maybe? I think that's in order. Let me start with slide 6 here. This is an empty means random intercept model. So note that I am naming each side specifically, and things in red are part of the model for the means, and things in blue are part of the model for the variance. Not to be confused with the acronym BLUE, Best Linear Unbiased something. There's BLUPs and there's BLUEs. Best Linear Unbiased, what is it? Expectation? I'm looking at you. Is that right? Okay. It's like Mr. Data Science over here. You're the representative of that side of campus. Yeah, not to be confused with that. It's just blue because green and red have issues. So, but green and blue don't. Or red and blue don't, excuse me. So in a standard cross-sectional model, we would have Y sub I and E sub I, because each person would have only one occasion, and an empty model would have just a fixed intercept. When we expand to multi-level land, then we have this structure where I pick up a T subscript for level 1 and I for level 2. Then I have E picking up a T and an I for the same reason, per occasion, per person. I have beta 0. Is that a fixed effect? It's a placeholder. Yeah, it used to be, but we're switching notational schemes here because this is now how each person is going to get their own intercept. It is a holder, a container. How that happens is then its own equation at level 2. So I think of this as like regression lasagna. Like there's layers of prediction happening at the same time, and they're all kind of melted together with a pile of cheese or something. So beta 0I is in black because it is not an estimated parameter. It contains estimated parameters. What's this thing? Gamma. I know the font looks weird, but that's what it's supposed to be. Gamma 0, 0 is the fixed intercept. And in this model, this is going to become the mean of the person means. So it takes on a slightly different interpretation than just the sample mean, because it's going to be weighted. If people have different numbers of observations, this overall sample mean will not match the mean of the person means, but they'll be close. U0 then is the same thing it's been all semester so far. That's our random intercept. So U0 is how far off your intercept is from the fixed intercept that everybody shares. So together, these create your intercept. And for those who are familiar with SEM notation in language, beta 0 is also a latent variable. That's how it is estimated in M+. The mean of the latent variable is the fixed intercept, and the variance of the latent variable is the random intercept variance. Once these things get figured out, beta 0 comes back down here, and we pick up E. So then E is how far off you are at each occasion. Question?
Yes.
Or-
Lisa, that random intercept, you are saying that that's the person-specific deviation from predicted intercept.
Mhm.
The overall intercept, right?
Right now, this is the only thing predicting the intercept. But more
Okay.
generally, as we add stuff, U0 will always be off from what's predicted based on the fixed effects in beta 0, predicting beta 0.
Great. And that is the prediction specifically, well, the specific prediction for each person,
Mm-hmm.
right?
For each person.
That's not the same as saying that that's the person-specific deviation from the predicted outcome, for example.
That is correct.
Those are not synonyms, right?
I do not think so. So let me repeat that for the recording. So I have person-specific deviation from predicted intercept specifically, not predicted outcome, because there's layers to this thing. So U0 is how far off your intercept is from the one that's predicted by the model. Right now, the model only has this in it to do that prediction. But by the end of the semester, we'll have some other person-level predictors in here. So that gets you to your predicted intercept. Then E is how far off you are from the actual outcome. So there's two steps to this, dividing up the total variability into two piles. Part that's due to who you are, constant person mean differences in this model, and then what happened today, remaining residual deviation from that person mean at that particular occasion. Zooming back out. And if you want to write it in a composite form without the placeholders in the way, then this little equation right here would give that to you. So in parenthesis, I have the part that would be due to beta 0, and an extra space for no reason. There we go. All right, Zoomers, are we okay so far? No chats yet, so making sure. Okay, Thumbland, Roomers, we're okay? All right, so this is empty. This model would be consistent with picture A here. There's no fixed effective time, there's no random effective time. So we're assuming everyone shares flat parallel trajectories. What's not in the picture would be the little dots, like around the lines, but I didn't want to clog it up. Then we added fixed linear time. So this is slide 12. So we pick up then beta 1i. That is how each person is going to get their own linear time slope for change over time. And right now, this is defined only as a fixed effect. So the beta 1 is kind of unnecessary, but we include it for parallel structure in the notation. So gamma 1o, why are the subscripts 1o? Do you remember talking about this?
The 1 describes beta 1.
Yeah, the 1 is because it's predicting beta 1. That's correct.
And the 0 is it's the only thing predicting beta 1, right? Or the first thing.
Yeah, it's the first thing, and we start counting at 0 in these models. Another way to say it is that this is the intercept of the slope equation, which might make your head hurt or it might make it better. Eventually, we'll have the intercept of the intercept, the slope of the intercept of the slope, and the slope of the slope. That's how it's described in the HLM literature, and that makes my head hurt. It's like, no, I don't like that. Yeah, no. Let's call this starting point for how each person gets their own slope, and we start counting at 0. I think starting point works better. This is not only the starting point in this model, but the ending point. It's fixed. Everybody gets the same slope. So this would be consistent with picture B, where there is some kind of linear change on average, but everybody changes the same way. That's what this model would predict.
And the time here is a categorical variable?
No, time, this is a continuous variable. So we are fitting a linear slope through whichever time occasions each person has. And each person could have their own set. That's why we have a TI here, because it can vary. So we're thinking of it in long format data where it's one row per occasion, and then it's whatever time you have. Now there was one caveat about time here. We need to make sure that time 0 is somewhere within the span of this data set. Otherwise, you can end up with problems of estimation once you add in random slopes, and we'll talk about that in just a minute. But time 0 at the beginning is most common. Doesn't have to be at the beginning, wherever you'd like. If you put it at the end, then all of your time observations would be negative. Like age minus 18 would give you a 0 at 18, but then everything before it would be a negative number. Works out just the same. Okay, so effect size. Here's a general rule, folks. Fixed effects explain variance. Random effects just make new piles of variance. So if we add a fixed slope of time, that trickles itself down into the level 1 model. It should explain E-variance. So time is a time level predictor. Therefore, it should account for level 1 within person variance of the residuals. How much? That's what we can figure out. So there are two families of effect size I'm going to teach you in terms of talking about how fixed effects contribute to the model. One is specific and one is general. So the specific one is known as pseudo R-square, and as you might imagine, based on the name, it's not an exact science. And by the way, this isn't me being funny, making up words or anything. It is called this, pseudo R-square. It's also called pseudo R-square in generalized models where there's not a true residual variance, because then there's a bunch of different ways to compute these things. So this is analogous to R-square in single level regression, but the thing about regression is that how many different piles of variance were there, like in a standard general linear model? Just one. So if there's only one kind of variance, how many R-squares could there be? One. Guess what's going to happen? In our model, yeah, this. I'll take that as a gesture. How many do we have right now in this picture, this equation? How many different piles of variance or variance components? This is a finger question, too. We got 2. We got vote for 3. How many blue things? 2. Yeah, so then how many R-squares could there be? 2. There's 1 for every variance component, and that's the idea of pseudo R-square, is how well did we do per equation, essentially per variance component. And if I have a linear effect of time in my level 1 model, that should explain residual variance and reduce the diagonal of the R matrix accordingly. So here is a formula in a sort of generic language. Pseudo R-square is whatever the variance used to be in the model that had fewer parameters before adding a fixed effect, so an empty model, for instance, minus what it is in the model that has more parameters, so after adding fixed linear time, divided by what it used to be. So my shorthand for this, you will hear me say repeatedly, is that the formula is was minus is over was. What was it before minus what is it now divided by what it was. I will teach you how to get these computed for you in Stata and R, and there's a shorter version of the formula that results in less typing that I'll use for that. But this is I think, the more conceptually meaningful version. So this is proportion reduction in residual variance, essentially. And by the way, this is the same way it would be computed for adjusted R-square in standard general linear models, because we don't have sums of squares anymore in this land. If your time variable also has between person variation, then it could conceivably reduce random intercept variance too. Now, when that would happen would be like an accelerated longitudinal study where people start out at different ages or different grades. That part of it would reduce level 2 person variance, And then the remainder of how much they changed over time would reduce level 1E variance instead. We're not going to do this semester, but it's in chapter 10 if you're curious. This will be one of the first things we tackle in the advanced class, though. However, what we're likely to see this semester for sure, and likely in life, is that any time that you explain residual variance, your random intercept variance is going to go up. Here is why. What we get on the output for level 2 random intercept variance is not just the variance of the person means. It's been corrected for the expected contribution of just random noise. So I'll explain it to you this way. Let's say that I take everybody in the class and I assign you to groups of 3 people each. And I tell each group, compute the mean height of your group and tell me what it is. Are all of those group means going to be the same? No, they shouldn't be that different because I randomly assigned you to groups, but they're going to wiggle a little bit based on the 3 people who happen to be in your group. Well, this estimator, I should say, is trying to account for that by saying how much would just be expected to be there just because of whoever shows up, in your grouping versus how much is actual signal beyond that noise. So their proxy for noise is the level 1 residual variance divided by the level 1 sample size, so the number of occasions per person in our case, on average if there's different numbers. So the observed level 2 person random intercept variance is a function of what it truly is plus noise. To try to estimate what it really should be in truth, they subtract off the noise. So the observed variance that you could compute across the person means minus the residual variance divided by level 1n as a correction factor gets you to what the output says is true. So here's what's going to happen, for instance, using some numbers from example 5. Let's say that the observed level 2 person mean difference variance is 4.65, and my level 1 residual to start with is 7.06, and I have 4 occasions. Well, if I feed that into the formula, then the result would be the true part is 288 for what's at level 2. The rest of it is just noise. Let's say that I include a fixed linear time slope, and there is systematic change on average, so it does reduce the residual variance all the way down to 2 from 7. So in terms of proportion reduction, 7 minus 2 divided by 7 is about 70% of the variance explained at level 1. Well, now, when I feed the new version of the residual variance back into this equation, the end result is actually higher because you're subtracting off less noise. So I wanted to explain this to you so that when you see it on your output, you don't think you did something wrong. You didn't make your model worse. This is a natural consequence. Anytime you explain level 1 residual variance, your level 2 random intercept variance has to go up at least a little bit. The question is, do you see it, right? So if I had 50 occasions, I wouldn't see as much of a change as if I have 4. But you will see a net increase to the extent that you've explained a lot of residual variance. So that will happen. All right. Do I want to do this next? I don't know if I want to do this. Let's look at an example. How about we do that? Let's get you going on what you can do for your next homework. By the way, the next homework is data analysis, but literally the goal is for you to figure out the syntax and find things in the output. It's just a word search, right? Find the random intercept variance, find the slope variance, Like that's the level the next homework will be, because that's step 1, is figuring out where the numbers are. And it is surprisingly non-trivial to figure out where all the things are, especially across 3 different programs. So to help you practice that, these are data from the book. So this is the example 5 is based on chapter 5. So all the numbers and everything will match exactly. I made up these data. I have deliberately made a small sample of 25 persons here. In the last part of this, so this handout is 26 pages long. I don't want you to freak out. We're not going to do all of that in class. The second half of it is all of these same exact models using structural equation modeling software instead. And I will make a video or use the one from last time. I'll have to see if I can do that. That's separate outside of class as an additional for your FYI. That way, if you haven't had that content, you won't be missing anything. So this is Stata code to start with, of course. I am telling it where my stuff is, importing the data in Excel format this time. In terms of data prep, there's only one thing I need to do. I'm going to center time. So the variable in my data set is called wave, and it's 1, 2, 3, 4. I'm subtracting 1 from it to generate a new predictor for time, in which the first occasion is the 0 value. So centering time. Stata folks, I have this commented out, but this may be helpful for you in figuring out what some of this code is doing. This is a new addition to this class, and actually all of my classes. I finally cracked the code to make Stata do math. Finally. It was surprisingly challenging. And this was part of the code. These commands, essentially, after you run an analysis, if you run these, it will tell you everything that has been saved for you that you can access. So that can be helpful. So first step, data description. So I am asking for a description of the wave predictor, and the full reason to do this is because I'm going to need the variance of time in order to compute something later on. So I'm asking for that, and I am saving it. So in Stata, I am essentially creating a new object called timeVar, and it is out of the variance that I just asked for in the summarize command. So rvar is what Stata internally calls the variance it is storing after summarize. And it's one number because there's only one variable. I can check to make sure that it was assigned correctly by just saying display, and then we refer to the variable with this $sign in front of it, and it turns it this kind of aqua color in the code. So then this would print what it shows, what I just saved here. So this is very much parallel to what happens in R when you save objects and access them. The only catch is that this is what it's called. To refer to what it is, you have the $sign in front. So to invoke it, so to speak. I also am saving for later computations the number of occasions as a variable called n times, which is 4. And what is the highest time value? That will be 3, because my time vector goes 0, 1, 2, 3. And then I found some code that someone else made to make a spaghetti plot, or a plot of individual trajectories. So I have that here as well, if you'd like to make pictures out of your data. Okay, Stata folks, any questions on that much? All right, R folks, I didn't forget about you. So I'm picking up a few new packages relative to what we've seen before. I had to use ggplot2 to make spaghetti plots in R. We're still using NLME. We're adding in Elmer test, which is going to also load the LME4 package, because we're going to use Elmer for some of these models as well. And Lavon is how you do structural equation modeling in R the easiest way. So that's for the second half of the handout. Usual steps in terms of setting the working directory where my files are. I'm reading in the data set in Excel format, making sure it's a data frame, and then sorting it so that I have like by person and then by wave. I'm centering time at the first occasion by creating a new variable called time from wave -1. And then doing the same in terms of data preparation steps. Describe is the descriptive statistics out for this time variable. And I want to save the variance of it like that. The variance of time, by the way, is right here. I put that in a comment. And I'm also creating a new object for the number of occasions that will show up in computations later. So the idea is that I'd like you to be able to repurpose this code without changing a lot of things manually. So like there'll be computations where I'll have the number 4, like for the number of occasions. If you save that here, then it updates everywhere in the code, and you change it once instead of multiple places. I finally figured out how to do such things in Stata as well. Very proud of myself for that. Okay, and here's the pictures I made. See? They're pretty. It's blue. So this is the fake data set. I know, 25 lines. If you have a lot more people than 25, you might want to plot a random sample. But what are your impressions? What's happening over time in these fake people? Yeah, they're going up. Are they all going up the same extent, do you think? No. So just eyeballing it, it looks like they're going up on average, some people more so than others. And the consequence of that, does this look like a homogeneous variance pattern is going to fit this model? Or do the variances look like they're changing too? Eh. And if the variances are changing, the covariances are changing. So yeah, pictures like this would indicate, yep, this is heterogeneity of variance over time. Odds are good, I need more than a random intercept in this model. And these are the kind of plots that you would put in a poster or a conference presentation while you're talking about your data set, just to give people a chance to visualize it. Maybe not in manuscripts, but possibly. I have a disclaimer. I am having to use like in this example, 3 different functions in R to be able to make this work, because one thing does not do everything I need. So this is my disclaimer on why I picked what I picked. But the first thing we can look at is the answer key. What are the patterns we're trying to recreate with respect to the means over time, and then with respect to the pattern of variance and covariance? So because this is a data set with balanced time, I can estimate this model and find out. So the model for predicting the occasion means is right here. Oops, then there's a typo. What'd I screw up? Wave 3 is missing its subscript. Yep. My bad. So underscore TI space, and then it becomes a subscript. Have I showed this class how to make equations in Word yet? Not yet. Would you like to see that real quick?
Yeah.
Yeah, I think it makes your papers look nicer. Let me get a new one open. I'll make some stuff. Here we go. Okay. So the equation editor is under Insert. I think you can do equations. I'm used to doing the keyboard shortcut, which is Alt equal. Then you get a thing that looks like this. And so in the equation, type your equation here. I'd like to. There we go. So I start with a y. Y needs subscripts. You don't have to go hunt and peck for the formatting menu with this. It is essentially the same as LaTeX. It uses the same types of commands. So I'm going to type an underscore and then a TI, and then I'm going to hit enter, and it jumps to be a subscript like that. So I hit the arrow key to get out of the subscript, then I can hit the equals. Now what comes first if I'm writing, say, an empty model? Let me get this over here. Trying to make it big. There we go. Way bigger. What comes first? Beta 0. And it's lowercase beta, right? So I'm going to hit the slash that's above the enter key. Is that forward or backward? I never know. This one. And then the lowercase word beta. And then I'm going to hit a space bar, and it jumps to be that. So the key is the slash. Then it recognizes you're trying to do notation. If I needed an uppercase beta, then I would spell it that way, and that's what I get. But I don't need that. I need a subscript. I'd need an O and then an I. There, like that. If I wanted to do a superscript, for instance, if I want to make a variant sign, like sigma, space, the caret is how you do superscripts like that. Hit space, and then I can still do a subscript with the underscore like that, and hit space. So the inline equations that you can do as special characters, you can do some of them, but you cannot do ones that have both subscripts and superscripts very easily. So I usually use like the equation thing for that rather than just the special characters in generic font. So this will make your things look nicer. And then for whatever reason, this I didn't want to be in italics, so we'll just fix that. There we go.
I have a question about this. I know this isn't necessarily the content of the class, but then would you just copy and paste that into your paper? Does that mess with the formatting of your, because Word is not very nice when you do different things, so.
So what I would do, let me back out of this so I get to the end of the page here. When I do equations, the way that I do it is like this. I make an invisible table. It's visible to start. I drag this over here. So let's say that I wanted this to be my equation, and this is going to be equation 1 in my paper. Then you can take the table and hide all of the lines to it, and it just looks like that in your paper, but then everything stays aligned. So if you do it that way, it's separate from the text and it shouldn't screw anything up. I would also use bookmarks, by the way, to make your life easier. So the way that I do that here, like I'm going to highlight this, and I have these saved, but I believe they are under references. Insert bookmark. Where is that? It's somewhere up here. That's what I'm looking for, like that. I'm going to name it, so this will be like empty model is tied to this number 1, okay? So I'll hit add, and then that means down here, when I am typing and I want to say equation 1, I don't type 1. What I do is go up to here with the insert menu. Hang on, where'd it go? And it should allow me to insert that bookmark, the 1. And so it's a reference to the 1, not the 1, because that way when equation 1 becomes equation 2, eventually after you start revising, it updates all the references. So I would highly recommend this for equations, table numbers, and figure numbers, anything that could move around where you don't want to have to fix it in every single spot that it's referred to. So, all right, little professional development today. We'll mix it up a bit. Why not? So yeah, this, you can see that it's an equation because it has this box around it. So this is an inline equation, this one. So point being, what we have is a saturated means model. Wave 2, 3, and 4, these are binary predictors that turn on and off when we're talking about each wave. So that means beta 0 is going to be for wave 1, and each of these tells us how that wave's mean differs from this one. So we have as many fixed effects as we have occasions in a saturated means model. So the object here is to figure out what the average trajectory looks like. I did that in my book. Yeah, I did. I had to figure out all this stuff to be able to do that. Although my publisher made me use a different equation thing, so we'll have to see if that is still the case for the revision that I'm ostensibly working on. Ostensibly. So I have highlighted then the parts of the code to pay attention to, since there's a lot of code here. So this is Stata code, and in R I am using GLS, which is from the NLME package. That is the only way I know of in R to make an R-only model. Eventually, it's good, but this one plays nice with LME, so that's why I'm using this instead of MMRM, which is the other one that I had found for the others. So I dot in Stata means treat this as a factor variable, a categorical predictor. It's the way it does the dummy coding for you. I still have the no constant because I don't yet have a random intercept. This is the unstructured model, so I'm trying to figure out what the pattern is. So that's what I have for the residuals command here. Note that I have wave to make sure that if I had any missing data, the rows get assigned to the right spot based on the data that they do have. Asking it to print the R matrix and the correlation version of it. Asking for an omnibus test of mean differences over time and what those means are. Making a picture of the means, saving said picture, and then getting mean differences by wave. So whatever's happening is notated in the syntax here. In that. And I believe you've seen most of this before, but are there any questions on Stata code thus far? Good? Okay. In R, so I have factor wave here because wave is not stored as a factor variable in the data set. I'm just converting it to that for present purposes. And then this mess is how you tell it type equals UN. Never ever would have figured this out on my own. But this part, core sim, gets unstructured correlations, and then weights equals heterogeneous variances. I know, like, all right, sure. And because it doesn't give you -2 log likelihood, I asked for it, and then I asked for the summary that has everything else. So I have in this handout a mix of R and Stata, but only both for certain models. So this one is R, because the Stata output is much more transparent. So this is the interior of the R-core matrix is what it's giving you. And then it gives you the variances as these weird multipliers of the standard deviations. No, thank you. I'll make it work. Here's my coefficients, and I have them labeled for you. So the mean at the first occasion is 10.4. It is 1.4 higher at the next occasion. Relative to occasion 1, wave 3 is 3 points higher, and then wave 4 is 5 points higher than wave 1. So this is an ANOVA model. essentially, saturated means. This is not a slope through it yet, because we're trying to ascertain what the pattern of mean change is to figure out what kind of slope would be a good match. I asked for the R matrix out of this with the function getVarCove. This is the name of the model that I'm pulling it from. Individual, this is the specific ID value of my first person. So like if I had subject numbers that started at 100 or something, then I'd have to do that instead. So this number is specific to this data set. Marginal means give me the overall pattern. In this case, there's only one possibility because everything's in R. So marginal is the only choice. I'm asking it to print it, and then I'm asking it to turn it into a correlation matrix. And then note in here, this is the number of occasions, so that would be the number of dimensions you need for one person. So rows and columns here. So here is the answer key for the variance pattern over time, where this is the total variance at each occasion that we're now going to try to figure out what pattern we can use to structure this. So eyeballing these numbers, you think the variance is changing over time? We got 2, 4, 6, and 11. I'd call those different, and it's changing in a pattern. The variance is growing over time, not just sort of bouncing around. That's informative. Covariance is also changing over time because in part of the change in the variance. So I come down here to the correlation pattern. What would you describe these correlations over time as? Same or different? We'll start with that. I'd say different. Somewhere between 0.46 and 0.91. So the first and last occasions are still fairly well correlated, but undoubtedly the ones that are closer together have more of a correlation. So those are the patterns we're going to try to mimic. I'm asking for an F-test. So this is my ANOVA omnibus test of mean differences. I am then asking for EM means, gives me not just means, so that's the first part here is what it's generating. Pairwise equals wave, or squiggle wave, excuse me, means all possible pairwise mean differences. I'm not worried about alpha inflation today, but I do want them to be tested using Satterthwaite degrees of freedom, so I included that with this. So here are the means as predicted from the model. So it's just doing the math for you to put these back together again, and I have notated what exactly it's doing here. And then here are all the mean differences. So all 6 mean differences are spit out at once. This is the linear model's representation of how they got there. So Erica, I'm making the other class do this the hard way, but this is the easy way. Yeah, so yeah, I'm making them do everything with like lincoms and stuff, so they get used to the coding pattern, but you all know how to do this by now, so I'll take it easy on you. We have enough to do otherwise. And I made some pictures. So I saved the means out of EM means. I then created the summary of them as a data frame. And then I found some code from someplace else using ggplot to make lines and saved it to a file. And I did the same thing with the saturated variances. I saved that information from the R matrix into a new object, and then I stuck them together so that I'd know which occasion is which. And so then here is the depiction of the mean change over time. So looks like folks are heading up. And this is the change in the variance over time. So note, this one looks fairly linear, I would say. Not perfect, but fairly. Would you call this one linear? Not really. There's a reason for that. Stay tuned. Dun, dun, dun. I'm a big fan of foreshadowing. What if you can't do the answer key? What if you have unbalanced time or too many occasions relative to the number of persons? Well, you could always round time into nearest occasions so that you could print that. If you still can't do it, I could at least do a saturated means model and then a random intercept. So I could get the answer key with respect to the model for the means, what the fixed effects are trying to recreate, but not necessarily the model for the variance. So I wanted to show you what that one would look like too. So this one has R output as well. No, Stata output. Look. Did I do both? I did do both, that's why. There. Now it's both. Problem solved. So the difference in stata is right here. I highlighted the colon in yellow because there's no constant after it. That means I've put the random intercept back in. That is by default. So this person right here, this guy. Residuals is back to independent because this is a GNR model. So now we have a random intercept variance in G, and then R is diagonal with residual variances only. Stata prints the fixed intercept at the end, but otherwise this would be the same estimates as before. Standard errors are going to be different, though, relative to the unstructured model. Here is my random intercept variance as a parameter, so that's 4. Residual is 2.2. We're going to ignore this for right now. We'll come back to that later. And here's my V matrix. So the V matrix in this case, 4 plus 2 is 6. That's how I got my diagonal. And then the off diagonal is formed with just the random intercept variance. So this model says there's only one source of covariance across occasions from the same person, and that's person mean differences, and that's it. If I needed to turn this V matrix into correlation, then I can do that more readily by asking for ICC, and that's what it is. Question? Did I miss a hand? No? Okay, just waving, or thumbs upping. The thumbs up icon and the question icon are very similar. And the applause icon too, that one. So what does this tell me? 0.65, do a little reviewage.
64% waste of time?
Not this time, I would say, but yes, 64% is between or within? It's between, yep. This is the proportion of total variation that is due to person mean differences. It is computed as 4 divided by 6 and some change. Did I have the math for that out here? Sometimes I put it in, not this time. There we go. Here's my F test for mean differences. Note that the degrees of freedom are larger now because it's essentially dividing this into between versus within. Same thing with the margins, same standard error across time because this model says the variance is constant across time. And the same thing with the pairwise differences. Those are assumed to have constant standard errors as well. Our folks, this same model would look like this, but welcome to a new function. This is LME inside the, you would think, the LME4 package, but no. LME lives in the NLME package. You just got to know this. It's crazy. I know. And the reason I'm showing you this one is that LME is the only way I have found that allows you to have both random effects and some kind of pattern in the R matrix. So the code for it looks a little bit different. You still have to tell it what data set you want. Method equals REML instead of REML equals true. It has separate equations, or excuse me, I would say, what's the word I want? Nope. Arguments, that's the word I want. Separate arguments for fixed effects and random effects. So the fixed side says outcome is squiggle 1 plus wave is a factor variable. And then I have random equals squiggle 1, and then a bar with person ID. So that's how you tell it what your nesting structure looks like. I'm asking for -2 log likelihood to be printed, which is not a default, and then the rest of the summary. So LME output looks different, which is why I wanted to show it. Note this thing right here. It gives you standard deviations instead of variances. As far as I know, there's no way to override this directly. But you can get them back out of the object if you'd like. So the first number is for the intercept. That is the standard deviation of the random intercepts across people. The second number is the standard deviation of the e's across occasions and people. And then here are the fixed effects, the mean for wave 1 plus each of the subsequent mean differences. Now the nice thing about LME is that there's a ready function to get you a V matrix if you want one. It's getVarCove. Now marginal means something. So when we have a G matrix, which is what we have here, with the random intercept in it, that's between, our R matrix becomes what? If the between part has been removed, what's left? Within. So marginal means put them back together again. Show me V. Total is another word I would throw into that idea. So what it's labeling as the marginal variance covariance matrix, we're calling V in this class. That is the same thing that Stata's command W correlation / covariance. That gets you the V matrix out of Stata. But there's no way to easily compute an intraclass correlation. They don't have that as a function that I can find. So again, I made one, and by me, I mean Jonathan did. Transparency. I figured out all this data stuff myself, though, so he didn't help me with that. I do know a few things every now and again. So there's my interclass correlation of 0.65. So the most readily, I think, interpretable way to think about that is in terms of proportions. So 65% or 0.65 of the total is due to between-person mean differences. The other way is as a correlation. This is the average correlation across occasions from the same person. Got my F-test, got my means, which I did not print because we've already seen those. All right, 124. How are we doing? Maybe cautiously optimistic? So here is another way that I could estimate this same model. This is LME code. And again, the reason to use this would be if you want something in your R matrix that's not diagonal, some kind of residual correlation pattern. If you don't, though, there is another option for you. And this one is called LMER, or Elmer, as I hear people pronounce it. And this one is from the LME4 package. So if you took clustered multi-level with me last year, we only used this one. The reason for that is because if you have persons nested in clusters, there is no other R matrix besides diagonal that would make sense. Because people are just sort of arbitrarily, this is person 1, this is person 2, this is person 3. They're exchangeable. Whereas in this class, time 1 is not exchangeable with time 2, is not exchangeable with time 3. So R matrix patterns are a possibility for longitudinal data. If you don't want one, though, you can still use Elmer. And its code looks a little different. So data set, I have Rummel equals true. Can you guess how I would modify this to make it maximum likelihood flavor instead? False. Yes. Very good. And this one does not have quotes around it. Whereas like in LME4, Rummel has quotes around it. Like seriously. Back here, where'd we go? Lost it, here we go. And all of the fixed and random effects are stacked into one thing in Elmer. So I've got formula equals my outcome variable is a function of a fixed intercept plus treating wave as a factor variable plus a random intercept in parentheses, like that. I'm asking first for information criteria, so this AIC tab gives me both log likelihood and something called deviance. Deviance is your -2 log likelihood. So this is the number you put into the homework if you're using Elmer. Random effects are given both as variances and covariances. Or excuse me, variances and standard deviations, that's what I meant to say. So I have, this one's for you, because this one's the variance and this one's the standard deviation, and then this one is for E. And here's the same fixed effects that we've seen. There is a way to get an intraclass correlation out of Elmer, but it's from a different package. The package is called performance, which to me seems really optimistic. But thank you, whoever made that. And they give you two different kinds, adjusted or unadjusted. Unadjusted is from the empty model. Adjusted is from your model that you just asked for. So you can see what the effect size would be for dependency after controlling for predictors, which is what interclass correlation is another way to think about. It's the effect size for how much dependency is caused by the random intercept. To do f-tests for the model for the means, for instance, I had to switch functions. ANOVA. This is sometimes likelihood ratio tests, this is sometimes f-tests. It's contextual. And I could have used, I have a note over here, joint test could have been used, but it kept switching the degrees of freedom method and would not let me override it to what I wanted. So I had to find a way around it, and I did. So I'm using ANOVA to get the f-test that goes with the mean differences in my saturated means. And then here's all the follow-up means and mean differences as from before. Okay, questions on any of that? I know I'm going through it relatively quickly. But again, your next homework is find this number. And you can see why that is a non-trivial assignment. Okay, we're good? Good-ish?
I think as soon as I start to try to do this at home, I won't be good anymore.
You won't be good anymore. Well, let us help, is what I can say. Or give it a try, and then let the homework system tell you if you're on the right track or not. All right, so let's do some multi-level stuff. Empty model. Here's my equation. So my outcome, which is the name of the variable that it is here, it's deliberately generic, is a function of beta 0 plus my e at level 1. At level 2, beta 0 is composed of a fixed intercept and a random intercept whose variance will estimate, and then the composite would look like this. So in Stata, first off, this one has Stata output only because the R output is relatively transparent. Note what Stata gives you right here. This is log likelihood. So you'd have to multiply it by -2 or use my little thing here. So this is an example of a post estimation. This number has been stored automatically. So immediately after you run an analysis, if you run this, it will do the math for you to print the -2 log likelihood. So that is my workaround for that. My fixed intercept is 12, which is gamma 0. My random intercept variance is right here, and my residual variance is right here. And I have a note here that Stata is giving you a likelihood ratio test, and what this means. So this is a likelihood ratio test using a mixture chi-square distribution. This is something that I will talk about towards the end of lecture 5, but I have a brief explanation as to why it's different right here. In our case, though, the critical value is essentially what you would get if you fit a single level empty model. That is what it means by linear model, like general linear model. This is the likelihood ratio test against that model. So it would be significant without the mixture chi-square or the standard mixture chi-square, either way. So this is essentially the significance test that goes with the interclass correlation. What would happen if we didn't have a random intercept? This is how much worse the model will get. Significantly worse. Here's my interclass correlation that I asked for. So it's down to 0.29. So this is the unadjusted correlation. This is 29% before we do any prediction is due to between person mean differences, and this is how I computed it. So the 2 divided by the 2 plus the 7. So all of this you've seen, I think, before in some way, shape, or form. Does this model seem okay? Empty models. Maybe? It will be. By the end of the semester, this will be easy. You're like, oh, I like the empty model. I got that one down. So I am going to do some extra stuff here to save pieces of output by which to compute a pseudo R-square. I know that I'm going to be adding a fixed linear slope of time, and that this will be the baseline model I need to compare against to see how effective that fixed linear time slope was in explaining level 1 variance. But this is tricky. So in my Stata code, right after the command, I did this. Matrix is a command that says, hey, make a new object. And my object is going to be called empty RI, empty random intercept. Equals R table is a summary of all of the estimated parameters in your model. So the first thing I'm going to do is figure out where the stuff is that I want to save. So matrix list means matrix print, and this is what I get. The first row is the estimate. The second row is the standard error. Here's my corresponding t-value, p-value, lower confidence interval, upper confidence interval, degrees of freedom if appropriate. This is some kind of critical value based on your sample size, and I don't know what this is, but it's zeroed out. So 12, that one's easy. 12 is right here. So that means, okay, the first is the fixed intercept. That seems reasonable. Then I get to LNS1 underscore 1 underscore 1 colon underscore cons. Excuse me? What the hell is that? I don't know. But this one is LN sig underscore E, which seems more prescriptive. I bet that has something to do with residual variance. So I look at this number, 0.97, and I'm expecting it to be 7 for the residual variance, and it's not. Because what Stata estimates directly and then shows you in this matrix is the log of the standard deviation instead of a variance. Apparently that's easier computationally or numerically. Well, I'm like, what am I going to do with that? Found some help online to turn it into a variance. So I have e to the that unlogs it and then squares it. And so I am now saving a new object called empty resvar that is going to be containing the 7 so that I can do math on it. And if you're thinking to yourself, can't I just get my calculator out and compute this pseudo R-square? Yeah, you totally could. However, if you write your code in such a way that you don't have the specific numbers, then you can recycle this code and compute an R-square for any other problem. The only catch is trying to figure out where the thing is that you want to have. So this is actually the random intercept variance. This is the log of the standard deviation of it instead. This is the residual variance. So I'm saving this one number as a new object, and then I'm printing it to make sure that my code worked, and it did. Okay. R folks, here's your version. So Elmer, empty model just has a 1 where the fixed intercept is and a 1 for the random intercept. Asking for fit statistics and the summary, as well as the intra-class correlation. So that will generate all the expected output that we just saw. To do likelihood ratio tests using Elmer. That's not ANOVA. That is something called RUNOVA. And now I have to make my joke. Whenever I try to use Elmer, I feel like I've been run over. Shh. I'd say thanks, I'm here all week, but no, I'm leaving next week. I will feel like I've been run over after I've been on a plane all day long, I think. And this means, tell me what it would be if you took out each term in terms of the model for the variance. So it gives you a likelihood ratio test for like all the combinations. So that will give us a likelihood ratio test for the contribution of the random intercept. I am then doing the same trickery in terms of saving objects. So varcore is a function that gives me the variance components in the model. I'm saving it as a data frame so that I can then figure out where the residual variance is in that matrix, and I found it in row 2, column 4. So I'll show you what that looks like in the next model. But this is how I save the same information. Empty resvar is now containing essentially the 7 of the value that I'm eventually going to want to use to compare it with. Okay. Do we have enough energy for one more model? And maybe 1 R-square? I'm like, oh, I don't know. It's dubious. I'm not going to see you for like 2 weeks. I know. We can do it. We can do it. See, I knew this would be this point in the program, so I was like, here, look, this spot, yellow. That's what's different. So I'm adding in continuous time. CDOT means treat this as a quantitative predictor. So I am not estimating saturated means. I am estimating one single linear slope that is to go through the means. That's what I'm doing instead. I am storing the results of the model by which to do a likelihood ratio test against the next one. I am storing the results of the fixed effects and the variance components so I can do math on them. I am printing the -2 log likelihood, and then I'm asking for model predicted means at each occasion. So plugging in the fixed intercept plus the fixed slope times the value of time at each occasion. And margins is a faster way to do that. Note that I'm using a macro variable here. I already told it that that's 3. So now I can just say go up to the last occasion, and I don't have to customize my code any further. Doing the same trick, showing the saved results, figuring out where in the output my residual variance is, unlogging it and scoring it to turn it back into a variance, displaying it to make sure I got the number, and now I can do my pseudo R-square. So 1 minus the model that has more divided by the model you started with is an alternative version of the same formula. This is the version that I think is more intuitive, but this one's less typing. So it's a slight rearrangement to simplify it. And the full output for all the models in both programs is in the download folder, so you can always check that out. In R, oh, I forgot to highlight it. It's right here. Time. There, problem solved. So the Elmer output then, here's my -2 log likelihood. I've got my variances and standard deviations for the variance components. Here is my fixed effects table. So the intercept now is at time 0. So 10 is the predicted mean at time 0. And my time slope says what? Not a trick question. What's a slope do? A change in y for a 1 unit change in x. So if we put that into the story, what happens to y? Goes up by 1.7 per? Yeah, unit time, whatever that is. And so unit time is generic language. If I were writing this in a paper, it'd be per week, per month, per year, per decade, whatever the unit is. Do the work for the reader and tell them. Yep. Then I'm making predicted means. This is a new function called contest1d that works with Elmer. It's in the Elmer test package. It uses the same multiplier principle. So 1 multiplies the fixed intercept, and then the second number is what you want to multiply the time slope. So it's essentially filling in this little equation right here with these commands. Here is the saved result of the variance components as a data frame. So this is the number that I want. This is the residual variance. So it's in row 2, column 4. So I save that, I compute pseudo R-square, and then I get the 0.69. Ta-da. We did it. 141. And we'll go back over it again too, because we'll need to re-go over in 10 days, I suspect. All right. Questions before we call it a week? No?
I know that I'm confused about pseudo R-squared.
Okay.
But I might go see Vladimir this weekend or something and ask for that.
Okay, or you can chat with me after class, and the next class doesn't start till 2. So, okay. Then, folks, please work on your formative assessments. I'll let you know when homework is ready and when there are videos you can watch to do some more next week. But in the meantime, have a break from me. Thanks for being here. I'll see you on the other side.